finally, I'm so excited. We can get back to what we talked about on the first day of class, right? We talked about the tangent problem and the velocity problem, and I said these are very important problems that we're going to be learning how to do calculus so that we can do these problems. And the reason it took us 4 whole weeks to get to it is because in order to do these, we need to know how to take the limit. So all that stuff we were doing last week and at the early part of this week too, about taking the limit to a point, taking limits to infinity, this, that, and that all comes into play here. And in fact, we've already done some problems which will look very similar. So now we have to give context to it though. So the context is the following, right? And if we get back just to the idea, let's say here's some point A, right? Let's call it P, right? It's some point P, A, f of A. And I want to take the tangent. Remember what we had done, we would take some other point, PQ, when we would look at the secant line. So the slope of secant line PQ, this say was at some other point X. So f of X minus f of A over X minus A. And then, as we did, and we'll show it in all the videos and whatever, we took this Q and we moved it all the way over and over and over until we had a tangent line. So the slope of the tangent line, then now we have the language is the limit as x goes to a of this secant line. In the velocity problem, similarly, but different context, but similar math, right? Because we had some function s of t, and this is the distance. And then if I wanted the average velocity, and I'm going to use the x and the a. So between t equals a and t equals x, we can do average velocity. So the difference between the distances over the difference in time, right? And if we wanted the instantaneous velocity at t equals a, essentially we were making this time step smaller and smaller and smaller, right? So now with the notation of limits, we can write velocity instantaneous, which then would be the velocity at time a, is going to be the limit as x goes to a of f of x, oh sorry, it's s of x minus s of a over x minus a. So you see, it's the same form, right? This form actually has a name. It's called the difference quotient. And there's this, and then there's a slightly different form of it that we're going to use more often. But first of all, I want to say, so both of these problems, and then there are other problems where this comes up as well, sort of rate of change problems. Anywhere where we're talking about something changing with respect to some other. So there's lots of different problems where this comes up, but these two historically are what people were looking at when they developed calculus. And so this thing then was given a name, and the name is the derivative. Okay? So let me write that up. This is the definition of the derivative. The derivative of function f of x at x equals a is, that's this limit, right? Limit as x goes to a and it has a notation we use f primed of a. And there's another notation we use as well, but we'll talk about that in chapter 3. So we're just going to use f primed of a. Notice it's a prime, it's not a 1. And that's the derivative. And this is called the derivative when this limit exists, right? Because we know that limits don't always exist. And a lot, in fact, we'll have plenty of examples maybe next week where that limit doesn't exist. So then you say the function has no derivative there or the function is not differentiable there. So we'll see that a lot. But when the limit exists, then we say that this is the value of the derivative. Okay? There's another form that we use probably more often than this. This one I use typically in the problems with the velocity because it so nicely looks like the change, right? The change from the average velocity to the instantaneous velocity. So we'll see this form as well, but more often we can make a little change of variables. Get rid of that x for a moment. The idea being, if I'm looking at my graph, instead of doing a and x, I'm going to do a and a plus h. And then if I let h go to 0, this line goes back to that one. So if I change that, then what I have is this form of the difference quotient. As x goes to a, that means that h goes to 0, like we did in our little thing there. So limit as h goes to 0, and then f of a plus h minus f of a over h. A, because you get a plus h minus a there, right? Because x minus a is h. This is the form that we'll almost always use. And if you actually remember from the worksheet from last week, that problem with the h in, it was one of these. It was one of those limits. We didn't say it was the derivative, but it was one of those limits. And another one was, I think, of this form. It had a square root of 2, I believe. No, maybe not. Yeah, it is square root of 2. So from last week, there were 2 homework problems or worksheet problems that were both computing the derivative. So as I said, it's something you've seen before. We just didn't call it that. Now we're going to use the right words, and we're going to show you what it's good for. Yeah, that's fine. Next, I'm just going to launch into a whole slew of examples.